Example 8, heating of water by resistance in a tube. So this is the question. Water is to be heated from 15 degrees Celsius to 16.5 degrees Celsius as it flows through a 3 centimeter internal diameter, 5 meter long tube. Figure will be shown after this. In the next slide. The tube is equipped with an electric resistant heater that provides uniform heating throughout the surface of the tube. So from this statement, we know that this is uniform surface heat flux cases. Okay. The outer surface of the heater is well insulated so that in steady operation, all the heat generated in the heater is transferred to the water in the tube. If the system is to provide hot water at a rate of 10 liters per minute, so we have the flow rate of water. Okay, determine the power rating of the resistant heater and also estimate the inner surface temperature of the tube at the exit. So here we have to determine the power rating. The power rating is the same as joule. Power rating is joule per second, or in other words is watt. Therefore, in order for us to determine the power rating of the resistant heater, so we have to find what is the Q, rate of heat transfer for this system. Okay, so to estimate the inner surface temperature, we have to use the equation under the uniform surface heat flux for TS, to find TS. Okay, so this is the question figure, and we have 15 degrees Celsius. A fluid temperature enters to this 5 meter long pipe and then exit at 65 degrees Celsius. So we have electrical heater constantly, okay, heating to the water inside, the fluid inside, okay. The diameter of this tube, okay, is 3 centimeter. So from here, we have to find what is the properties of water. The properties of water will be evaluated at mean temperature, bulk mean temperature, where the equation for the bulk mean temperature is Tb equal to T inlet plus T exit and divided by 2. So we have 15 degree for T inlet and 65 degrees Celsius for outlet. We must sum up these two values and then divide by 2. So we get the bulk mean temperature is at 40 degrees Celsius. Therefore, you have to see the table E9 based on the properties of water. And you have to find what is the rho density, thermal conductivity, kinematic viscosity, specific heat capacity, and Reynolds number. Because all of these properties will be used in our calculation. Okay. Now, before I go to solve this question, I would like to emphasize on the entry length. So if from the previous example 7, I've already shown you on the calculations of the thermal entry length, which falls under laminar flow. If you want to calculate the entry length for the laminar flow, after you get your Reynolds number and then you compare with 2300, if the result your Reynolds number below than 2300 and you have that is laminar flow. We know that in laminar flow, there is two regions. Either it is fully developed laminar flow or developing laminar flow, developing entrance region. So here, in laminar flow here, so this is fully developed turbulent flow. If your laminar flow falls on fully developed flow, then your Nusselt number would be 3.66. Okay, if this is fully developed laminar flow, LF, fully developed laminar flow. So here is developing entrance region. Okay, developing lamina entrance region. Okay, DLER, developing lamina entrance region. At this point, your Nusselt number would be Nusselt number under developing laminar flow. So you have 3.66 plus and so on. At this point, before the flow start to fully develop, the Nusselt number would be different as x increases. So this is a graph. If you can memorize or if you can revise back and try to find this graph, okay? So this is Nusselt number. As the x increases, the Nusselt number would be decreases. So this is your, let's say you have your Nusselt number is 37.6, and it will reduce up to 3.66. And after it fully developed, it will constant. The Nusselt number would be constant where it is 3.66. This is fully developed laminar flow. And the importance of you to find the entry length is to know either your laminar flow, you decide, you calculate Reynolds number and then you compare with 2300. You just only says that it is a laminar flow, but you do not know whether that laminar flow falls under developing laminar flow or fully developed laminar flow. So to understand this or to know this, you have to calculate the entry length. So that's why from the previous example 7, I try to find what is the LT, thermal length of this laminar, of that laminar flow, and we found that it is about 100,000 compared to your 200 meter cylindrical pipe. Okay, and your total length of the pipe falls under the entry length of your laminar flow. Therefore, you have to use the equation under developing laminar entrance region. Okay, the step is like this. First, you find your Reynolds number, and then you have to compare with Reynolds number, either it is below than 2300. If it is below than 2300, it is laminar. This is your previous example 7. And under laminar flow, there are two regions: developing laminar entrance region and fully developed laminar region. Okay, how to know whether your tubes is under developing or fully developed? You have to calculate the entry length. So calculate the entry length from your Reynolds number and then plug in all the values and you will get the Reynolds number. So from the previous example, your Reynolds number, your LT laminar, I think is about 100,000. Okay, and if you compare with your length of cylinder or tube, 200 meter. So your entry length is 102,000 meter and your length of cylinder is about 200 meter only. So your cylinder is totally in the entry length. So therefore, you have to use the equation in the developing laminar entrance region. If you calculate your LT is about maybe 0.3 or 6% below than total length of your cylinder. Okay, then you can disregard the entry length and you can assume your cylinder is fully developed laminar flow. Then you can take out the value of Nusselt number of 3.66. Okay, you will not have any equation or values to be substituted into the equation because the Nusselt number at fully developed laminar flow is constant at 3.66. Okay, and it is around 6% or maybe 10% and below because it is too small. 0.3 meter out of 200 meter. It is small compared to 200 meter and you may neglect that value. Okay, and it is the same as turbulent flow. If your Reynolds number is turbulent, you cannot say that it is a turbulent flow. Okay, sorry, yeah, you cannot say that it is a turbulent flow because there is a developing laminar flow where there is an entrance region, and as I mentioned before, the entrance region normally laminar flow. Okay, so to calculate the thermal entrance region for the turbulent flow, you have to substitute into LT turbulent is equivalent to 10 diameter. So you substitute into this and you take a look at the LT turbulent flow. Okay, if your length of the cylinder is much more greater or length of this turbulent flow, thermal entry regions of that flow is much more smaller than your total length of your cylinder. Okay, you can assume that your cylinder or your flow is fully developed turbulent flow. Okay, understand? Fully developed turbulent flow where your Reynolds number is greater than 10,000. This is fully developed turbulent flow. So why this is important? Because you want to use the equation that falls under fully developed turbulent region here. This equation. This equation, this Bolter equation, is only can be used for the Reynolds number which is greater than 10,000. So you may assume your Reynolds number is and obviously for the calculation you will get the Reynolds number beyond than greater than 10,000, maybe 15,000, 20,000, 1 times 10 to the power of 6, you will get the Reynolds number greater than 10,000. And you calculate the LT here, LT turbulent, take a look at the entry length and then compare with your length of the cylinder. If it is too small, then you may assume that the whole length of your cylinder is fully developed turbulent flow. Then you may use the Nusselt number equal to 0.023 Reynolds number to the power of 0.3 Prandtl number to the power of n. And n here, it depends on either it is heating process or cooling process. I've already mentioned and I explained about the heating and cooling process in my previous video. Okay. Okay, that is all for the introduction of this, the introduction for the example, this example, and then we go to calculate, okay, and answer this question. Okay, first is we have to find what is the Reynolds number. So Reynolds number equal to or maybe you can you might not need to find what is the Reynolds number first. Okay, because we have to find what is the power rating of the electrical heater. So we have to find what is Q first. So we have to find what is the Q. Q dot. This is power. This is rate of heat transfer, which is equivalent to power rating. So here, from the figure, we do have volumetric flow rate, okay, and then we have T inlet, okay, 15 degrees Celsius, and then 65 degrees Celsius. From here, we can actually use directly equation Q dot equal to M dot Cp Te minus T inlet, because all the information has been given in your question. So you have to substitute into the equation. So your M dot, from here, we in the question, we already been given by Q or V dot, which is volumetric flow rate, where the volumetric flow rate is 10 liter per minute. Okay, so to change into the meter cube per second, so 10 liter per minute times with 1000 liter is equivalent to 1 meter cube times with 1 minute is equivalent to 60 seconds. Then you will get, this is how much? So maybe I will remain it as a meter cube per minute. So we have 0.01 meter cube per minute. Okay, this is the volumetric flow rate of your question. So in order for you to get mass flow rate, we know that mass flow rate is rho VA. So velocity times with A, this is mass flow rate, density. So from the equation of density, we know that density is mass over volume. If we can change this, rho VA, mass flow rate, oh sorry, from this equation, density, I will not use this equation. We can actually use this equation because V times with A is equivalent to Q. So, or V dot. So, from here, density is mass over volume. If we change this into mass flow rate, then this will be mass flow rate. So, rho is equal to mass flow rate divided by volumetric flow rate. So in order for you to calculate what is the mass flow rate, density must be times with volumetric flow rate. So your density is 992.1 times with 0.01. So you will get 9.921 kilogram per minute, or we can change into per second, which is equivalent to 0.1654 kilogram per second. So you already get your mass flow rate. Then substitute into this equation. So your mass flow rate is 0.1654 times with Cp, specific heat capacity, which is 4.179 kilojoule per kilogram dot Kelvin, times with 65 minus 15. So from here you will get your Q dot is 34.6 kilojoule per second, or 34.6 kilowatt. So this is the power rating for your electrical heater. Okay, electrical heater power rating is the same as Q dot. Okay, power rating for electrical heater is equivalent to 34.6 kilowatt. Okay, that is the first question. Let's move to the next question, where we have to find what is the surface temperature of the fluid of your cylinder. So from here, from equation of heat flux, we know that Qs equal to H Ts minus Tm. So we can rearrange this equation. Ts equal to Q dot S over H plus Tm. Okay, that is the question, equation on how equation to find surface temperature of your question. Then we want to find what is the Q dot for this question. We know that Q rate of heat transfer is 34.6. Heat flux is equal to Q dot over A S. Okay, so now your Q dot is 34.6 kilowatt divided by, so surface area is 0.7471 meter square. So to find surface area, AS is pi dl. So you have substitute into this and then plug in into this to find what is the heat flux of this question. Then you will get the 73.46 kilowatt per meter square. So that is your heat flux. So now we want to find what is the Reynolds number in order for us to determine whether this flow is actually a turbulent flow or a laminar flow. And then we can decide either it is in the developing laminar flow or fully developed laminar flow or fully developed turbulent flow. Now what we need to do is to find what is the Reynolds number. So from Reynolds number equation, so V average times with diameter, divided by kinematic viscosity. Now we have to find what is the average velocity. To find average velocity, we have to calculate it from volumetric flow rate. We know that volumetric flow rate divided by cross-sectional area. You have to remember that volumetric flow rate area is cross-sectional area because the flow of the fluid is by cross-sectional, not surface area. So surface area is only for heat transfer. Okay. So your V dot is 0.010 meter cube per minute, and we divide by 7.069 times 10 power of minus 4 meter squared. Then you will get 14.15 meter per minute or 0.236 meter per second. So you have to substitute into Reynolds number equation. So V average is 0.236 times with diameter 0.03 and then divided by kinematic viscosity. So you will get your Reynolds number is about 10,760, and this is turbulent flow. So from here, we need to check, or you can check either this flow is actually, is it the entry length is half of that flow, of that length of the cylinder, or it can be assumed that the whole cylinder is fully developed turbulent flow. In order for you to determine or assume that the fully developed turbulent flow for the whole of your cylinder, you have to check with the entry length, the entry region. So now you know that when you compare with the turbulent flow, where Reynolds number must be greater than 4,000, and this Reynolds number falls under this region, and this is turbulent flow. Okay, so now we want to find under turbulent flow, can we assume that this is fully developed turbulent flow, or it is a developing region? So how to do that? We have to substitute into this equation. Now we have turbulent flow. We want to find what is the thermal entry length by using the equation of 10 diameter. So now we substitute into this to find what is the LT. Is approximately 10 times with 0.03. So this would be 0.3 meter. So 0.3 meter compared with your total length of your tube is 5 meter, is about 6%. Okay, and therefore we can actually assume the whole of your we can assume your flow is fully developed turbulent flow. Therefore, you already assume that your flow is fully developed turbulent flow. Therefore, we will use the equation by this person, Peters-Boulter equation, where we have to substitute the value of Reynolds number and Prandtl number, power of n. Now we want to find what is the n. So we will use Dietz-Boiter equation. Okay. So the Dietz-Boiter equation is what? So Nusselt number equal to 0.023, Reynolds number power of 0.8, Prandtl number power of power number of n. Now we want to find what is the value for n. So we have cube and then we have 15 degrees Celsius and the exit temperature will be 65. So the exit temperature is 65 degrees Celsius. So we want to find either this is heating process or cooling process. As we can see here, this temperature, the temperature of the fluid increased from 15 to 65. Then the Q has been absorbed to the system. Therefore, the N here is for heating, where N to be used is 0.4. Therefore, you have to use Nusselt number equal to 0.023, Reynolds number 0.8, Prandtl number 0.4. Substitute into this equation, you will get your Nusselt number, which is 69.4. Then equate this Nusselt number to Hd over K to find what is H. So your H is 1460 watt per meter square dot Kelvin. Okay, previously we already derived this equation. Okay, to find Ts, we have to find what is the heat transfer coefficient. We already done this and we already found the value for the heat transfer coefficient. Qs also we already determined it, which is 73.46, and then T mean temperature is we will take T exit as our mean temperature here. So here, so Ts is equal to Tm plus Q dot S over H. So our Tm here, mean temperature here is T exit. I will take T exit as our Tm. So Q dot S over H. Now I substitute the value to find what is the T surface for our question. 73460 divided by 1460. And it is equivalent to 115 degrees Celsius. This is T surface inside, okay? It is not outside surface temperature. So it is equivalent to 115 degrees Celsius. We already answered our question. Okay, thank you.